Hey guys, welcome. If you don't know me, I'm Brandon. Some of you know me if you're local in the Seattle area. Some of you don't. That's totally cool. Quick background on me. I've been with Lego a long time, not with Lego, but building Lego. And for about the past 10 years, I've been teaching elementary school about engineering and robotics and other curriculum using Lego. So I've picked up a lot of little mechanical things and have used them in my MOCs because I like the movement parts. People are always asking me about how I make it move, so I figured I'd throw together this basic presentation. I know a lot of you know how to make things move, but I'm hoping you'll still pick up something out of this that might help elevate everybody's knowledge a little bit. So we'll run through this and make things happen. Let me go ahead and share my screen, make this happen here. And if you got questions, hold on to them. If we run out of time, if we don't have enough time for questions, hit me on the side afterwards. I'm in Discord, or you'll get my email here. You can always follow up with questions. Happy to do what I can to help everybody out. All righty.
I like to move it, move it. I like to move it, move it. I like to move it, move it. You like to move it. I like to move it, move it. I like to move it, move it. I like to move it, move it. You like to move it.
We'll just rock out here for about an hour. That's cool. Or not.
That's great.
So I got a quick itinerary. We're going to go through a lot of stuff. Typically, if I was teaching this in a class, this would be done maybe over the course of a year's worth of curriculum. I'm going to cram it into 40 minutes, 45 minutes for you guys. So we're going to go quick, but we'll get through it. Trust me, I can make it happen. I can make it always happen. So first thing we're going to talk about, Lego that moves. Very cool thing that Lego that moves. So 1963, Lego came out with their wheel set. Wheels move. That's Lego that moves. Maybe that's not what you're thinking about, and neither am I, but it is Lego that moves. So that's where we start. In 63, Lego came out with their gear set. Really cool gears. They could move, and you could connect them to your wheels. So now you got gears and you got wheels. We'll talk a little bit more about gears in a bit here. 1966, Lego came out with some motors. The first motorized sets in 71, a reversible motor set. The reversible motor set in 71 actually has an axle that connected to the wheels to make the treads move. They didn't have Technic yet, but that was kind of the cool first stepping stone into the world of moving motors, moving Legos. In 1977, this is what the world looked like. Some of you might remember this, some of you might not. But yes, Orlando Bloom was born in 77 and Elvis died in 77. In 1977, Lego looked like this. Very blocky, very bricky, very cubish. The minifigures were just starting to come out, but Lego sets, basically, it was brick, a lot of cubage. But in 77, they also introduced these new technical elements, new sets that look very, very different from their bricky, blocky friends. So the question has always been, is Technic actually Lego? If you're not familiar with it, it's very different. You got things with holes in them. You got pins, you got pegs, you got axles, you got gears, you got these weird things. But the wonderful engineers at Lego designed it to work with the regular brick. So you can fit your Technic pieces together with your regular pieces, and they all work in a beautiful, seamless system together. So I know some people are like, I'm afraid of Technic. I don't do Technic. It's just Lego. It just connects different ways, but it is the same system. So try not to be too afraid of it. It's your friend. It's okay. Okay? So Technic basics. If you know Technic, this will be easy. If not, you might learn something. Basically, Technic fits together instead of just studs on studs. You've got pins and holes. The pins go in the holes, okay? And that's how you hold brick together. There's many different ways, but that's the basic concept there, okay? Pin basics, I used to think these things were the same thing. Oh yeah, little black ones, little gray ones, they're just different colors, like all Lego is just different color. But no, they're actually a little bit different. And now I've misplaced my thing, there it is, cool. So the friction ones are black and they fit tight. The non-friction ones are gray. I'm going to stop my video here for a second And just wanted to demonstrate that real quick, because I worked with Lego for 40 some odd years before I figured this out, and it wasn't explained to me in any way. And I don't think the sets really explain it. But if you have a Lego beam, let's just say, and you have a gray pin versus a black pin, if you connect something to the gray pin, I don't know if you can see that, my background's messed up, but it moves, it wiggles, it's very loose. If you connect to the black pin, it's tight and it holds. So the gray ones are loose. If you want to build something that's going to move and be free, use the gray ones. If you want something that's going to hold tight, maybe a bridge or some structure that's got more friction, use the black ones. Hopefully that helps somebody, because it helped me once I learned it. So that's basics, very, very basics. Beyond that, you have different sizes. You have the short ones, which are 2 studs, go through 2 beams. The longer ones, the 3 ones, go through 3 beams. And then you have the ones that's a combination of a pin and an axle, or a paxle, or a combination pin. Come up with your own weird name. Uh-oh. When did they come out with the black ones? Yeah, they have black ones. They came out a long time ago. Sorry. Mind blown. I hope you're not being too facetious there. We'll get there. We'll get there. So if you understand these basic 6 pin types, short ones, long ones, and axle ones, friction ones and non-friction ones, you're set. There are lots of other pin configurations, but these 6, in my mind, sort of set in motion the foundation of pin connections. There is also a half pin that has a stud on one end, which is great for connecting other elements to, just like a regular stud. And then there's a 3/4 pin, which fits into half-thick elements, which I'll say that for another time. That's more complex. Okay. Axles. Axles slide in and rotate through the holes. Yes, they go in the hole. Sorry, they go in the holes and they spin around like that. That's how the axles work. Real basic. Axles come in different lengths. We talk about them by how long they are, by how many studs long they are. Generally, the black ones are even numbered stud spaces. 2, 4, 6, 8, 10, 12, 16s, and 32s. And typically, the gray ones are your odd sizes. There are exceptions to that, but as a general rule, you can sort of identify lengths by color types until you get to the red ones and the green ones and the white ones and the yellow ones. Then it gets all weird, but stick with that. Okay. So that's just sort of Technic in a very, very, very quick nutshell. If you're not a Technic person, I hope maybe that helps you a little bit to tip your toe in the water and try some Technic stuff, because that's basically it. There's lots of other crazy stuff, but that's the basics, basics. All right, simple machines. If we want to talk about engineering, a simple machine is just a mechanical device changing the direction or magnitude of a force. You push, you pull, you lift, you twist, you do something, you change that force in some way, and you're going to be using simple machines in its most basic function. If you take any machine, break it down to its simplest principles, you get these 6 simple machines. This is it. I didn't come up with these. In the universe of mechanisms and machines, this is it. There's 6 of them. There ain't gonna be no more. So use them. Wheel and axle, things that roll. Levers, there's 3 classes. That's another session. Belts and pulleys, wedge, screw, and the inclined plane. If I could say that with a British accent, I think I would, because it would sound more sophisticated. But the inclined plane is a very nice machine. Simple machines. Now, all of these machines have all kinds of cool, totally awesome mathematical properties and calculations that you can do to figure out how much you're going to be changing that magnitude or force, how much of a mechanical advantage you'll get or lose, what's going to happen. But we're not going to talk about the math because math is hard. Just think about machines, simple machines, change the direction or magnitude of a force. So if you're building something in a Lego, and you're like, well, my thing does this, but I want it to do this. Okay, you need to change the magnitude or the direction that that force is going. Let's figure out what we can do to do that. Okay? Now, a complex machine is just made up of 2 or more simple machines. And a gear is a great example of a complex machine because it uses some of the properties of those simple machines and makes a new thing that we can use. Okay? A gear, pretty darn cool. Now, when gears fit together, and I can't see everybody here, but I need everybody out there to hold up your fingers like this, like they're gears, and slide them together like the teeth of the gears are actually sliding together. Some of you aren't doing it. I lied, I can see you. There you go, excellent, thank you. So we call that meshing. Gears need to mesh. The teeth need to fit together properly, mechanically, to give the right amount of energy transfer. Too tight, it doesn't work. Too loose, it doesn't work. So we need a good mesh to make sure it fits just right. The spacing of the gears is important to make sure you get that mesh. I've seen a lot of builds where things go together and it looks like they'll work, and it kind of works, but it doesn't. And if you don't get that right fit, it's not going to give you the right functionality. Your machine's not going to be efficient. It's going to wear out or it's going to fall apart. So get good mesh. Don't mesh with me. Two gears sitting next to each other, they're going to turn in opposite directions. One goes clockwise, the next one goes counterclockwise. That's pretty easy. Gear transfer, typically when you talk about gears, you have one gear that's sending energy or doing the work. It's the input gear or the driver gear, and it's making the other gear do something. That's the follower gear or the output gear. Okay? So you got an input and an output. You make it do something, the other one does it. If you put a gear between those gears don't really do anything except pass the energy along. You're creating a gear train and you're just moving from the input to the output through more gears. Those are just idler gears. They're very helpful. They move things along. When we talk about ratios, mechanical advantage, those don't count, but I won't confuse you with that. Just know that you can put extra gears in the middle to move the energy along. Now, gears of the same size, they produce the same amount of speed and the same amount of torque. A motor or whatever your input device is going to have a set speed, and it's going to have a set torque. Torque is twisting power. Just how much twisting force is there in that mechanism that's moving. If you're doing a hand crank, it's however much torque you have in your little fingers. If you have a motor, it's how much torque does that motor have. So gears of the same size, you have an input gear of 24 teeth and an output gear of 24 teeth, magically, they're gonna turn the same speed, they're gonna turn the same number of times, they're gonna have the same number of torque. There is a little bit of energy loss, but we're not gonna factor that in. We're just gonna call that nominal, just little friction, the Lego rubbing on something. We're gonna assume it's good. You get some cat hair stuck in the axle, that wears it down, but we're not gonna factor that in. We're just talking hypothetical here. Okay. Now, if you change one of the gears and make one of the gears larger, let's make your input gear larger and the output gear is smaller, then you start to change the ratio of speed and torque. Now, speed and torque are inverse opposites, meaning as one goes up, the other goes down. As the other goes down, the other goes up. They're going to be inverse opposites. They're always going to move the same amount in the opposite directions. Always, always. So if we reverse those gears, we take the big one and we make it the output. We make the smaller one and make it the input. Instead of getting more speed, we're going to get less speed. And instead of getting weaker, it's going to get stronger. You have more torque. So just by changing the sizes of the gears and the orientation of input to output, your output can go faster, but weaker, or slower and stronger. That's kind of cool. We could again talk about the math. We're talking about a 1.67 to 1 gear ratio. That doesn't mean a whole lot if you don't know math. Now, if we change the gears a little bit and go to a 24-tooth gear to an 8-tooth gear, we're now getting a 3 to 1 gear ratio. That means it's going through, the output is 3 times faster than the input, but it's 1/3 the amount of power, or 1/3 is weak. Reverse those. Okay, now we're going 3 times stronger, but 1/3 the speed. Okay. If you crank it all the way up to a 40-tooth gear, to an 8-tooth gear, the math is pretty simple. 40 divided by 8 is 5. 8 times 5 is 40. So we have a 5-to-1 gear ratio. So we can make it go 5 times as fast or 5 times as strong. But remember, they're inverse opposites. So we can't go, oh, I want to gear it and make it go 5 times as fast and times 5 as strong. Can't get both. You get one or the other. Or you get that balance where it's the same. Hopefully that's not too much for you. But if it is, just remember, if you can, I have a hard time with it. Bigger gear, moving a smaller gear, less torque, more speed. The other one does the other one. If you build your machine and you're like, I want it to go really slow, and you put the gears in there and it goes really fast, just take the gears off and change them around, make them go the other way, and eventually you figure it out. If it's not going fast enough or it's not going strong enough, change your sizes around. Change it up. Try to find the one that works for you. You don't have to know the math properties to figure it out. You can just play with the gears, and that's okay too. You're not going to break too much. Okay? There are wonderful charts and things out there that show you exactly what mathematical properties are going to be. If your 2 gears are the same size, your output's going to be the same. Okay? If you change one, it's going to get faster. Change the other, it's going to get slower. If you want one of these, I can give you a link to where to find a chart like this. Otherwise, just play with it. All right, in the Lego world, there's a lot of gears. It's a lot of gears. Nifty chart. Cool, thanks. I'll get you a link to it. So gears that have axles, when gears mesh in parallel next to each other, the axles are going to be parallel. Okay, that's inline gear meshing, gives parallel axles. Spur gears are a gear that does this. There's 4 kinds of spur gears in the Lego world. 4 sizes, I should say. The 8, the 16, the 24, and the 40. That's it. So if you just want to do inline meshing, just work with these. Most of them mesh really well together in many, many different configurations. That's pretty easy. I could stop my slideshow there, but we got more time, so we'll keep going. Okay. Clutch gears are a little bit different. Clutch gears are used for gear shifting and for slippage. The 24-tooth clutch gear, the center part is designed to move with the outside part. Unless it gets too much resistance, then it slips and it can move independent. So if you have a light load, it can transfer the energy from the axle to the outside of the gear. But if that load locks up or gets bogged down or has too much resistance, the axle can still spin, so you don't burn out a motor or something like that, or break your machine. Gears that mesh at 90 degrees, okay, give you a perpendicular axle. So the axles go in 90 degrees, opposite directions, going around a corner. That would be your crown gear, your dog gear, gotta get a woof woof, okay, and the beveled gears. The beveled gears are basically, beveled means just to cut off the corner a little bit. So you've got a short, sharp corner, and you've just cut off the corner a little bit, the edge. So beveled gears are designed to mesh at 90 degrees, like this. The dog gears and the crown gears, they work inline or at 90 degrees. That's kind of cool. Okay. The double bevel gears, wait, I didn't do that, hold on. Double bevel gears, not double bevel gears. Double bevel gears, it's a bevel gear, but it's beveled on both sides. So you can bevel it this way, or you can bevel it this way, but you can also mesh them in line directly with each other, just like a spur gear. And you can even mesh them with spur gears, which is kind of cool. So you've got different sizes for your beveled and your double beveled gears. And like I said, they do kind of work with the spur gear. Very cool. All right, rack gears. Rack gear is a flat gear, except for the banana gear. I throw it in with the rack gears because it seems like a rack gear to me, but it's bent. But these change circular motion of a spinning gear into linear motion, something moving flat and straight. I don't have any of the banana gears, so if anybody wants to throw some my way, I'd love to play with one of those sometime. Worm gears. Worm gears are so awesome. Worm gear is a one-tooth gear. It's basically one tooth that just spins around in a circle like a screw. There's a short one, there's a long one. Lego has a beautiful little gearbox, which the worm gear fits into in the bottom, and a 24-tooth gear fits into the top. The worm gear is a one-directional gear transfer. You can rotate the worm gear to drive the other gear, but not the other direction. If you turn the 24-tooth gear there on the top, you cannot move the worm gear. The gear ratio is so steep there to give you such more torque, such slow speed. When you reverse it, it just doesn't work. It just binds up. So it's a one-directional gear transfer there. When you use these ones in the gearbox, your axles are perpendicular, but they're offset. So you get a little perpendicular offset there, which is kind of cool. I love these things. Differentials and turntables are other elements that Lego makes that have gear functions in them. We could talk differentials for 2 hours and still not understand it all, so I won't go there today. Okay. Splat gears, these are kind of cool. They're newer. They can mesh 90 degrees perpendicular or in line, but the axles don't attach to these gears. They go right through the middle hole, so you would have to use another Lego element to get an axle to attach to it. They're really great for playability because you can just move them with your fingers. But if you want to do something mechanical that's moving via a motor or something, you'll need to find a way to attach something to the gear to actually drive it. But that's cool. You can do that. I think you guys can figure that one out. So gears that mesh. That's a lot of gears. It's very overwhelming. It's very confusing. Don't get too freaked out by it. Okay. If you want to use a beveled gear, it's going to work with double bevel gears, and that's it. You're not going to use it with anything else. If you want to use a crown gear, you can use it with the spur or the double bevel gears. That's kind of cool. If you want to use spur gears, you can use them with any of these gears. And if you want to use the double bevel, you can use it with any of these gears. It's pretty versatile. I like those guys. If you want to use the rat gears, they can push on the gears, the double bevels, or the spur gears. And if you want to use the worm gear, you can make it work with these, except the banana gear. Worm gear is not going to work well on that banana gear. I would advise against that one. But most of the rat gears, yes. If you want to use the dog gears, you get to use the dog gears. It's the only thing it works with. If you want to use the splat gears, it only works with the splat gears. So simply, there's a Venn diagram of what gears mesh with what gears. I can talk about elevators maybe another time. The worm gears are pretty cool. Using them for elevators is really cool. There's also other ways to do elevators. We can talk about that. I'll see if I can work it in. If not, another time, or catch me on the side. All right, so we're on to motion. There's 4 different types of motion in the mechanical world. Okay? There's also, well, the motor gives you rotary motion. Okay? Motor spins in a circle. So if you have motor spinning in a circle motion, you can have a machine that spins in a circle. If you want to put movement in your MOC, figure out what kind of motion you want to have as your output. Okay? You have linear motion, something moving in a straight line one direction. Linear motion. Oscillating motion, motion occurring around an object that swings back and forth around a fixed point. Pendulum of a clock, a seesaw, things like that. Oscillating motion. And reciprocating motion is just like linear motion, except it goes one direction and then it goes back the other direction. It goes 2 directions, back and forth, back and forth, back and forth, back and forth. So 4 types of motions. If you're thinking about MOCs, think about what kind of motion you want, or a combination of different motions. Okay? So drive types, how are you going to make these things move? Assuming you have a motor, you can do a hand crank, but let's assume you put a motor on something. 5 different types of drive types that you can do in Lego. Pneumatics is another kind of a drive type, but that's a whole nother conversation. If you guys want me to do a talk on pneumatics, let me know and I'll do that maybe another time. Okay? So direct drive. Whatever the motor touches, it spins. That's it. That's pretty simple. Direct drive. Make it happen right off the motor. Gear drive. Okay? One gear pushing on another gear. We talked about that. You can change the speed. You can change the amount of energy through the torque by changing the gear sizes. But you have a gear moving a gear to make it happen. 90-degree gear drive. Move it around a corner. Maybe the direction my motor is going is not the direction I want my thing to be going, so I need to get it moving in a different direction. Okay, we can use some 90-degree gear drive. chain drive. Sounds like a biker or something. I don't know. Still using gears, but we're moving the energy from one gear to another gear through a chain, like a bicycle. Okay, so those gears can now be farther apart. They're now going to turn in the same direction instead of typically when they mesh, it's opposite directions. Again, you can use different size gears to change the speed of the torque. Belt drive uses a belt, not a rubber band. Those are different. These are belts. They fit in the groove of a pulley, and they transfer the energy from one pulley to the next pulley. The nice thing about belts and pulleys over chain is that if your output device binds up or gets jammed, the input can still be spinning, and that belt will either slip or break. But replacing a belt can be much easier than rebuilding your entire MOC that broke because something got jammed in there, like a kid sticking their finger in there. Not that that would ever happen. Belt drive, you can twist the belt to create opposite direction, reverse the direction just by rotating the belt, put a little crisscross in it. That's kind of cool. Okay. So you got five kinds of drives, 5 drive types. How are you going to get the energy from your motor to your output device? Use one of these 5 or a combination of them. Okay? So you've got 4 types of motion and you got 5 drive types. Got a lot of combinations right there to help you get through this. Okay. Mechanisms. Let's see, anything I need to know here? Mechanisms, a system of parts working together in a machine. So if you want something simple like direct drive, you don't really need a mechanism. But if you want to change the energy from a motor to your output and make it do something different, we need some kind of a mechanism. So can you guys see the moving video here? Is that coming through okay? I hope.
Yeah, looks good.
Thanks, Doug. So here, I'm going to go through a bunch of these different mechanisms just to kind of get you guys some ideas. Think about how you might use this in a MOC. The green axle is my input. The red thing is the output. The red thing is what's happening. Just a bobbing piston. I'm using a gear, but I'm using it more like a wheel. I have a gray pin, non-friction pin, going around the outside of the circle of the wheel. That's eccentric motion through a fixed point. Sort of gives me an oscillating motion, but it's also a linear oscillating motion, which is kind of a bobbing motion. That's weird, but it looks cool. Okay. There's another piston using a cam just to move up and down. Just pushes the axle up and gravity pulls it back down. If I did this one on the side, it would push it out and then it would just stay out there because there's nothing to pull it back in. This one, we have a linkage, which is a bar connecting 2 points, compared with the cam. Both of these are pushing up and dropping down. The cam has more of a push and then a sudden drop. The linkage is more consistent and linear, more smooth. Different ideas and mechanisms. Don't try to remember all of these because I'm going to give you instructions on how to build most of them. Okay. Rocking mechanisms gives us that oscillating motion, rocking back and forth. Rock on, rock on. Okay. Horizontal sliding mechanisms. Right? Now, what I'm showing here is reciprocating motion, but I'm cheating. Behind the scenes, when I did the video, I have my finger on the battery box and I'm pushing forward, backwards, forward, backwards, forward, backwards. So I'm really showing linear mechanism moving one direction, and then linear motion going the other direction, and then linear motion going the other direction. If you want to build a mechanism that actually gives you reciprocating motion, where you can just turn a motor on and let it go in and out, that can be done too. But I just wanted to convey the concept here. Just the concept. Okay. One of my favorites, the parallel linkage. I'm going to try to pause the video here. You'll see that the input drive here, the green one, is hitting an 8-tooth gear to drive a 24-tooth gear. That's on the back side. So that's slowing it down and giving it more power. The axle from the 24-tooth gear comes through and is connected to the yellow bar. So as that axle moves, that one yellow bar is going to move. The other yellow bar is mounted in parallel with it, so that the 2 points at the bottom are 3 studs apart. The 2 points in the top are 3 studs apart. So as those 2 yellow bars move, they are always parallel with each other. And the output coming off the end, that little red plate, is horizontal to the table, and it always remains horizontal to the table or parallel with the table. Parallel linkage. I love these. They're just so cool. They're just so cool. Maybe you don't think they're cool, but that's okay. Weird elliptical bar mechanisms. I don't know what you'd use this for, but it's pretty cool. Looks like the side of a train or something. Are there any train people with this? It's got to be a train thing. Yeah. But you could mount something on this that would then be lifting. Maybe you've got a row of ducks that are bobbing up. You could have it affect other things as well. Okay. Dog gears or knob gears, depending on your term there. These can be mounted 90-degree meshing or in line. Either way, they just transfer the injury. There's a little bit of slop between these. Depends on what you're doing, what you're driving, and whether or not they carry the torque well enough. Linear actuators do exist, yes. There is a Lego part that is a linear actuator. There totally is. Yep. Here we're using the crown gear, using a spur gear, an 8-tooth spur gear, to drive the 24-tooth crown gear. And it slows it down because the output is larger. Okay? If I reversed these, I could have the drive gear be that crown gear, and then the output could be the 8-tooth gear. It would go much faster. So the crown gear can be input or output. Yeah, linear actuators are slow. Sorry, I'm trying to keep up on the chat too. Ooh, this one's fun. A timing belt uses the chain, but linked in with the chain is the 3-stud wide tread link every so often. And it passes over 2 dog gears. And so the chain length, or the tread, pushes past the dog gears to rotate them about 90 degrees. It's not always exactly 90. There's a little bit of slop in there, but it's pretty close. But timing belts is kind of cool. This one I don't have in my instructions, but you can let me know if you want to see more about it. Okay. Here we're basically just doing some gearing. Okay. You can see the inputs driving a 12-tooth double beveled gear that then drives a 36-tooth double bevel gear. And the first red block is going slower. But then that same axle does the same thing again, drives another 12 to another 36 to slow it down again. Okay? So we're slowing it down and we're slowing it down again. It's compound gearing where you do it once and then you do it again. Okay? So we got a 3-to-1 gear ratio and then another 3-to-1 gear ratio. So we end up, our final output is a 9-to-1 ratio, if that makes any sense to anybody. But you can slow it way down or make it way stronger. Here's the worm gear in action. Remember I said you have to drive the worm gear. You can't have the worm gear be the output. It has to be the input. Ooh, pretty. This one's less maybe practical, but I think it's still kind of fun. It's just showing a sliding mechanism, okay? And then a lever mechanism. So the yellow bar that hangs down hits the blue table and causes a tipping or a lever mechanism to happen. Okay, that's kind of cool. I don't know if you use that in a MOC as much. It's got good playability, really cool. We talked about the turntables, making things move. Okay, we've got a 56-tooth turntable being driven by a worm gear. So the worm gear has to rotate 56 times before that thing's gonna go all the way around in a circle. We're not gonna wait that long. We got more stuff to do. But if you want something to move really slow and really strong, that's a good way to do it. Okay. Belts and pulleys, talked about those. Okay, different types of dry systems, moving the same speed, or you can change the size, bigger output, goes slower. Smaller output, goes faster, runs real fast. Okay. And we're back to some linkages here. I'm going to show you 3 machines here, 3 mechanisms. They're all the same mechanism. The only thing I'm going to change is how many studs apart the yellow linkage is on the red one. Right now it's 5 studs from the bottom anchor point up to where the yellow bar attaches along the red one where it says 5 studs apart. And you can see how far the bar moves at the top, how much throw or distance of movement there is. If I move that yellow one down 1 stud closer to the end point there, now it's only 4 studs apart, the throw becomes quite a bit larger. You get more movement, more swing back and forth. If we move it 1 closer, now we got a huge long throw. So we've gone from a throw about this far to a throw about this far, just by moving that anchor point ever so slightly. If I moved it 1 closer, it would actually, the throw would become so far that the mechanism would bend back against itself, kind of like pushing an umbrella against itself. It folds back and then it doesn't work so good. And then you get wet. So don't do that. Don't get wet. Wow, that's cool. Okay. All right, mechanisms. That's a lot of mechanisms. I hope those maybe give you some ideas and are some helpful things to look at and play with. Okay? To help you out with that, I've got instructions where you can build 14 of those mechanisms. So there's a link there, bit.ly or bit.ly if you know how to do that, /mechanisms by Brandon. The M is capital and the B's are capital. Mechanisms by Brandon. You'll get this slide which shows you all the pieces that you can pull out of your own stuff. Not that many. And step-by-step instructions for 14 different mechanisms. I'm hoping you can enjoy those. Just build a little thing, play with it. It might be just a little thing like this. You're like, ooh, look, Brandon taught me how to build this. It's really cool. Or maybe you got one of these. Like, ooh, look at this. Brandon taught me how to build this. It's really cool. I don't really care. Build some fun stuff. Just build a little thing. Understand how it kind of works a little bit. And then go, what can I do with this? It's pretty cool. That's cool. All right, hopefully that was helpful. Power options. Oh, I'm running out of time. Sorry guys, I'm running long. We know that got old power. In 1990, came out with power 9-volt motor, and in 93, another 9-volt motor. 2007, we got power functions. The main motor is a direct drive motor. They had additional motors that had gearing inside that would gear it for more torque. Okay, slowed it down. Okay, gave you more power. Lots of battery options. You just plug the motor onto the battery, turn it on, turn the battery on, and the thing goes. It's pretty easy, pretty cool. There are remote control functions. 2019, we get powered up. Same kind of thing. You got a direct drive motor, you got geared motors, except it's all Bluetooth control. You plug the motors into your battery boxes, and then you pull out your phone and you sync your phone via Bluetooth or a tablet to the device, and then you control it through your device, or you give it commands and you program it. But basically, same kind of thing, it's just the current version of it. Programmable systems, if you're into programming, Mindstorms, there's 4 versions of the Mindstorm systems throughout the year. The latest one just came out, Mindstorm's Inventor. You're going to program this on a computer or a tablet, send the information into the main brain, the main brick, and then it's going to execute those functions. WeDo is an older system, uses the power functions motors. WeDo 2.0 came out before Powered Up, but uses the Power Up technology. It came out in the educational line, but it's basically the first release of what became Powered Up. And then Spike Prime is the newer system, kind of a mid-range. If you think of WeDo as the bottom entry level of robotics, Spike Prime is kind of the mid-range of robotics. Mindstorms is the top dog of robotics. You got different systems there. They're all lots of fun. Okay? These are the currently available systems of robotics that LEGO is supporting. All the others are older. They don't support those ones anymore. They don't sell them anymore. They still have some support for them. Okay? Evolution of LEGO motors through the years. From 1966 up to 2020, there are a few others that I did not list here, but these are sort of the main ones that I thought worth at least mentioning. If you want to mechanize something, you can use any of these motors in any capacity. They're all available and they all work. So just kind of figure out what system you want to use and go with that. Okay, that's kind of cool. Some project examples. Told you I was going to run long. Darn it. These are things that I've built in my classes with my kids and just for fun over the years. Some of these move, some don't. Just some pictures and ideas. What would things look like if you put it into a mock? How would something move? I like that one. That one's cool. I want to build that. Teacher Brandon, how do I build that? Okay. Worm gears. Someone was asking about the elevator. Here's a worm gear on an elevator, but it's horizontal instead of vertical. Worm gear on an elevator, you're somewhat limited by the axle length, which can be a big limiting factor. And any deflection sort of pulls the worm gear out, which can be hard. Okay. I know there might be some great ball people out there. This is one I did after kind of seeing some great ball stuff. I went home and tried this one. It's kind of fun, just using a crankshaft. Not unique in any capacity, but just a fun idea. The bottom one here that's moving, I'm actually using one motor and I'm spinning the motor by hand, which turns it into a generator to generate enough electricity to drive the motors that actually cause the doors to open and close. Kind of cool. Oscillating motions. Lots of crazy projects. I'm going to move it. You guys have seen my TV. You know that. We don't need to go down that road, but it's there. We're not going down that road. It's there. Okay. But you can make
it. We got another hour.
We got another. We need a whole therapy session for that one. Yeah. This is one I had at BrickCon last year. There's 3 motors driving 9 mechanical functions through a whole series of mechanisms and a lot of gears to get all this stuff to move off of the 3 motors. That was fun too. So more knowledge. If you want more information on Technic, gears, motion, how things work, this is a great resource. These are 2 books. It's the same book, but it's just different publications. Beautiful illustrations. Then the website that Sarah has that gear ratio calculator that I showed, that weird chart with all the little numbers and stuff on it, as well as some online tools you can use. Like, I want to use these 2 gears. Where do I put them in a series of Technic holes to make them mesh properly? It's not 100%, but it's really pretty cool. So again, just a good resource that you can use. So real quick in summary, with not too many minutes left for questions, I apologize for that. I will take them on the side as much as I can. We learned about simple machines, axle orientations, meshing, the different gear types, different types of motion and drive systems, different power. You can do hand crank, you can do solar panels as well, and there are third-party motors out there that work very well. I don't know any of them, but I don't use them. And the different programmable systems. So as far as putting motion into your MOCs, in my time that I have, I'm afraid that's about all I can cram in there. So congratulations on getting through it with me. Thank you for sticking with me on it. And if there are any hot questions that maybe Doug has filtered down, I'll be happy to take them until they kick us out of here. Feel free to shoot me an email, teacherbrandon.lego@gmail.com. All right, Doug, what do we got?
I don't know how long we have. Probably like 5-10 minutes or something like that. So let's dive in.
Like 8 seconds.
Are there any classes that you know of on any of this sort of stuff beyond things at conventions like this? Sharon was curious. And I hadn't heard of anything, but I don't know if you have.
I don't know of anything for adults. I mean, I've been teaching this stuff to kids for years. I have kindergartners who understand speed versus torque better than most adults do sometimes because they've had a class on it. It's what I do. I do it through a company right now called Snapology. Not that I'm plugging them, but it's what I do. I've done adult events. I've done Microsoft team building events and different things like that. I don't know of any companies that do it traditionally, but I would love to have the opportunity to do more of it. And if somebody wants to do something, it's like, get together 5 of your friends, I'll come and do it. I did a birthday party for somebody who turned 35 and they wanted a Lego party where we did some cool battle track type stuff. So it's out there.
Okay. Thanks for that. So I answered incorrectly. It's asked if there are linear actuators, and I didn't know of any in Lego. What's your knowledge on that? Apparently there are.
I don't have any. I would love some, but I know they do make a linear actuator. It's a Technic part. It's kind of a cool part. Again, I don't have any, so I've never played with them. I've never even touched one with my hands.
Okay.
But they're cool. But yeah, it's a part that you spin something and it makes something move in and out. It's really cool. Oh, there's one.
Oh, the screw. Okay, the screw actuators I knew, but you still have to spin. But anyway, all right, cool. What else? There was a comment, torque versus power. I don't think we really want to get into it, but just so people know they're two different things.
Yes. Technically, they're two different things. In the basic level, torque is power. It's how much twisting power. You can have force, there's lots of different powers.
So actually, it was me that asked that. So it's actually, the power stays the same when you have a gear ratio. So the power is the speed times the torque. So if whenever you said power, you'd have said torque, it would be correct.
Fair enough.
I really apologize for pointing it out, but I don't. It's a wonderful talk.
It was a very polite
I'm not above
question.
learning stuff too, so that's fantastic. Yeah, in my world of 5-year-olds, power and torque, that's about as far as they can go.
Yeah, I hear you, but power, that's what power means. Power stays the same when you have a gear ratio. It's speed times torque.
There you go. There you go.
Okay, I think we
Ignore
answered
everything I said.
Yeah, throw away all of Brandon's materials. I think we answered this, that Sariel might have some information on doing gear calculators, but Todd was asking specifically about a 24-hour clock, if anyone had a link to something for that. Or...
I've seen some of those online. I don't have anything specific. It's a lot of mathematical calculations to get the gear ratios right, and to make sure that your drive system is going to be consistent and not wear down off of batteries or off of friction or torque. But yeah, it can be done to create a proper clock ratio. You just have to do a lot of gearing to make it happen. And you can compound those gears in many ways. Gear it up, gear it down, gear it up, gear it down to get the right output.
Okay.
Torque is rotary force.
There was a question on, do all of the motors work, or are there only certain motors that worked for turning them into generators by manually turning?
The ones that do it best are the older, the 9-volt, the little square ones. They do it best because they were internally geared for torque. And even the new ones that are geared for torque do it, but they don't do it as well. The difference is when it's geared for torque, the motor is spinning, so the output is a lot slower, but stronger. So when you grab the end and you spin it, it's making the motor spin a lot faster internally. So you're actually spinning the armature of the motor a lot quicker through that type of a gear or through that type of a motor. The motors that are direct drive, like just the basic power function or the basic powered up, they're direct drive, pretty much. They're not, but pretty much. That's technical. And so when you're spinning it at the same rate it would normally go, and you have to spin a lot faster to generate enough electricity to create that generator capability there. So the old 9-volt ones were awesome for that. It's sad what they did, getting away from those motors, in my opinion.
Okay, Steve asked this before, and we were telling him we don't think so, but do you know of any way to attach the, like the 9-volt power supply, you know, the train one, right, that you can to power functions motors, because they've got the 4-stud-ish connector. Yep. Can we connect those to the new motors?
The new powered up systems?
Yeah.
That's what I know of.
It's got to be like a converter, but...
Yeah, not that I know of the powered up, because the powered up has a new special proprietary connector.
Yeah.
I don't know of a way to connect those two there. I'm anxious to learn more about the powered up as well. But I really like the option to just take a motor, plug it into a battery box, and make it go without having to get an app and a device and a thing and program it. I like that for some functionality, but I also like the simplicity of just turn the thing on and make it go.
Okay, Josh is saying that people are making some third-party converters. That's cool. Okay, good to know.
Oh, you can cut the cable off and just twist the wires together. Sure, you can do that.
You can make it work.
Yeah, got some duct tape. All right, guys, thank you. Hit me on the email or in Discord, although email is probably easier. Guy, if you have a string there, and I'd be happy to answer any other questions. Thank you. And if you want more, let me know what you'd like. I'd love to help out as much as I can. You guys are awesome. Thank you.